Hey folks, today we're going to be covering networking essentials. This is part of our core concepts, which is basically material that we think you need either A, to put together a good design, or B, because your interviewer might ask you questions about in deep dives or in probes, and we want to give you all of the foundations for you to be successful in your system design interviews. Networking essentials has about 4 sections. We're going to first cover the basics. We're going to cover the OSI model and talk about how networking works fundamentally. Then we're going to go into each of the layers, talking from IP all the way up to Websockets, SSE, and gRPC, so you can be familiar with various protocols that are going to be important. We're going to talk a little bit about load balancing because the intersection between networking and load balancing is really important. And finally, we're going to wrap things up with a bit of deep dives on regionalization, timeouts, retries, idempotency, cascading failures, practical things that you're going to need in your interviews. Let's get going. Networking is usually thought of as a layered cake, where at the top are application layer protocols like HTTP and WebSockets. And at the bottom are physical layer elements like wires in a network. When we're talking in system design interviews, we're usually only concerned with a few of these layers, but it's important that you understand these layers and how they operate. They're basically like abstractions. So recall that when you're building an app, you're probably not moving voltages around to write to a disk. You're probably using an open command and a write command. And that enables you to think about the important pieces, like what your data looks like, as opposed to the mechanics of the underlying hardware. Networking works in much the same way. These layers build upon one another and provide features and functionalities that you'll need. The first layer that we'll be concerned with in system design interviews is the network layer. This is where protocols like IP and InfiniBand live. The vast majority of applications outside of AI labs will use IP or Internet Protocol, and we're going to go talk about that in just a moment. At the transport layer, this is where you'll see protocols like TCP and UDP. They provide some additional functionality on top of IP, like guaranteed ordering or reliable delivery, things that you're going to want to be able to rely on. And so we'll talk about those next. And finally, at the very top of the stack is the application layer. This is where layer 7 protocols like HTTP exist, or WebSockets. These are going to be things that are useful to you as a developer and also important as you're navigating various trade-offs of how your system actually functions and then what capabilities it has. This layering becomes a little bit more clear if we work through an example. So when we want to make an HTTP request, we want to make a web server request to a website, we're actually going to transmit a lot of different information between client and server. As an example, when the TCP connection is initially established, we're going to use what's called a 3-way handshake. There's going to be a synchronize, an acknowledgement of that synchronization, an acknowledgement of that acknowledgement. And then, and only then, is our connection established. After that, we can go and submit requests over that connection or that TCP stream. And then we're going to get responses back from the client. What you can see here is that these layers are building on one another. The HTTP layer depends on the TCP layer or the TCP connection being established. And the TCP layer assumes that it can depend on using IP addresses to route packets through the network. So the central idea here is that these layers help each other, and they also are oblivious to some of the details of the protocols that live below them. There's 2 important things about this for system design interviews. The first is that there is a lot of back and forth, and that means latency when we're setting up and initializing connections. The second thing that's important is that there is state here. We have a connection established and a connection that's terminated. And that connection is not incredibly cheap for us to set up. There's actually a lot of latency and back and forth. And we'll need to be considerate of how we manage that state throughout the rest of our design. We'll get back to this in a bit. Let's go through each layer of the cake and talk about the protocols that occupy it and also what it does. We're going to start with the lowest layer, the network layer at layer 3. And at this layer is Internet Protocol, or IP. The responsibility for IP is basically to give names that are usable to nodes on the network and allow routing. We have 2 types of names, IPv4 addresses, which are 4 bytes. You can see this in this notation, and IPv6 addresses, which are 16 bytes. They're actually arranged in 2-byte pairs. The main difference for these is that we've run out of IPv4 addresses, and we haven't out of IPv6. You'll typically use IPv4 externally because it's going to be more compatible, and then IPv6 internally because it's more modern. IP addresses come in two forms: public addresses and private addresses. Public addresses are known to the world. They're assigned by a central body, and routers are aware of them. So as an example, this is the range of addresses that Apple owns. All addresses that start with 18, this notation means the first 8 bits of the address are meaningful. That is the first byte or that 18. All of the addresses that start with 18 belong to Apple. And so what that means for routing infrastructure on the internet is if you see an IP address with 18, you can send it over to the routers that Apple owns. With private IP addresses, you can assign your nodes any name you want. The only important thing here is that you remember where they are and that your routers are aware of them. So an example of a private IP address is 192.168.0.1. It's probably the address of your home router. This is actually a special range, this 192.168. You'll see 16, so the first 2 bytes. That's allocated for local networks. And the whole point is to eliminate any overlap between private addresses and public addresses. What you don't want to do is give your toaster an IP address that also is used by Google, and then when you want to go and send a packet over to Google, it actually goes to your toaster. For system design interviews, you're going to see these public and private addresses in 2 places. Public addresses are usually used for your API gateway, for load balancers, for externally facing components of your design. And the key thing here is that people in the outside world need to be able to send them information. Private IP addresses are going to be used for everything else, all of your microservices, any other internal hosts. And you need to both allocate them and be aware of them. So if you're going to load balance between IP addresses, you've got to keep track of which host exists, where they are, and which ones you want to use. The next layer of our cake is layer 4, or the transport layer. With IP addresses in hand, I can send big packets or like a block of binary data to a host. But I'm usually missing 2 things. One is context. I oftentimes care about what application it's both destined for and came from. This is usually solved with ports. Also, I care about the ordering of packets and whether or not they were delivered. And these functionalities aren't provided by IP natively, but they are provided by some transport protocols. There's really 3 protocols that are in widespread use today: TCP, UDP, and QUIC. QUIC is a more modern substitute for TCP. It's increasingly being used for web traffic, and it has a lot higher performance, but it looks very similar in terms of functionality. So I'm going to ignore it for a minute to focus primarily on TCP and UDP. TCP is the default. If you're talking about system design, your interviewer is generally going to assume you're talking about TCP because as application developers, you're usually relying on TCP for most of your communications. So let's talk about TCP first and some of the guarantees that it offers before we go into UDP and where you might want to break out of that default. So TCP is going to give you some additional features on top of IP, like guaranteed delivery and ordering. The way that this works is when you initially establish a TCP connection or stream, you're basically saying, I've got a sequence, and you're going to be giving packets a sequence number. Then, as packets go across the network, if they get out of order or they're lost, both the sender and the recipient will know what happened in between. They've got the numbers to back it up. So if you had packets 1 and 3, you might be able to assume that 2 was missing, and you could go back to the transmitting server and say, I lost 2. Also, if you got 5 after you had just gotten 3, you're going to wait a second for 4 before you emit 5 to your application. That's functionally how TCP works. Now, TCP is awesome, and it's the default because it's reliable. The hardest part about networking is that if the network fails to transmit or things are lost in the transmission process, it can be hard to deal with failures. and TCP mitigates many of those failures. But note that while I can guarantee delivery in one sense, like I'll know whether a packet was actually received by the other host, I can't really guarantee delivery in an absolute sense at just the network level. This isn't going to tell me, for instance, if the data was written to disk. It's not really relevant for things like CAP theorem, but it is relevant from a practical standpoint about giving you an insight into what actually happened on the other end of the network. Now, while all these guarantees that TCP offers are amazing, they have cost, and their primary cost is in throughput and in latency. If, for instance, a packet is lost in transmission, TCP needs to retransmit it before it can continue. And if your two hosts are very far apart, that retransmission can take up a lot of time. There are going to be applications where you don't need those guarantees and you want higher performance. That's where UDP comes in. You can think of UDP like a machine gun. It's basically spray and pray. As a sender, you're going to write your data, you're going to wish it, a good voyage, and you're going to send it off across the ocean and hope it makes it there. And in most cases it will, and in some cases it won't. Now, that kind of seems like it sucks and it kind of seems like wishful thinking, but it actually turns out to be really useful in some applications. As an example, when you are doing video conferencing, you don't want to, if you drop a frame, to go back to the host and say, hey, give me that frame again. What you'll usually do is just drop that frame out of the view. You might stabilize the audio a bit and you'll keep going. That's not to say that you won't go back to the sender at any point and send them a message to say, hey, you're dropping the connection. Can you lower the transmission rate? But it is to say that you don't care as much about those individual packets. So UDP is going to be really useful for real-time applications or for lossy applications, multiplayer games, audio and video conferencing, sometimes live stream. In system design interviews, you may be forced to choose between TCP and UDP. And your default should definitely be TCP. The cases where you're going to want to use UDP are those where latency is paramount and you can handle those failure modes where a packet is missing or you get things out of order. If those two things hold, then moving to a UDP-oriented service can be really useful. Now, note that UDP isn't supported by browsers natively. So if you have any browser applications, you're going to need to figure out a TCP version to use alongside whatever UDP applications like a mobile app might be using your service. Now that we've covered layer 3 and layer 4, TCP, UDP, and IP, we can graduate ourselves to layer 7, the application layer, where we'll be spending the majority of our time. The first protocol at the application layer is HTTP, Hypertext Transfer Protocol, and it is the most popular protocol for a lot of applications. And it's not just websites. Even RPC or remote procedure call applications will use HTTP because it's very versatile and it's battle tested over decades. The way that HTTP works is simple text formatted requests and responses. A request looks like this: get/post/1. I'm going to tell it which version of HTTP, and then I'm going to send it some headers alongside my request. This get is actually called the method or an HTTP verb. And it tells me a little bit about my intent. Am I modifying data? Am I retrieving it? Am I updating it? The headers are a key value dictionary, and they can really contain almost anything. The HTTP standard has a bunch of headers that are widely accepted, like content encoding or accept encoding, but you're also free to define your own headers that you can use at will in your application. The HTTP response is going to include both the actual data that we want to transmit, but also a status code, which tells me was it successful or not, and some headers, which might indicate what format the data is in or the date that it was retrieved. One of the more important ideas behind HTTP is called content negotiation. When I make a request, I might tell the web server that I'm requesting it from what kind of things I can receive. I can accept compressed content, or I can accept certain encodings. Then in the response, the server's free to tell me what it actually gave me. I gave you compressed content, or you asked for compressed content, but I don't have it. I'm going to give you plain text content. This makes HTTP both backwards and forwards compatible. when new versions and new functionality are rolled out, new headers are introduced, and then servers and clients are able to negotiate what they want to use and what they don't want to use. The name Hypertext Transport Protocol might be a little bit misleading because it kind of makes the assumption that we're just retrieving web pages. But HTTP is much broader than that, and it can be used for building APIs, as an example. The most common way to build APIs on top of HTTP is using what's called REST, or Representational State Transfer. The way that REST works is two pieces. One, we're going to use those HTTP methods or verbs to describe what operations we're doing. Are we reading data? Are we writing data? Are we updating data? And secondly, we're going to focus on resources. And those resources are going to have URLs associated with them. So as an example, if I want to read user ID 1, I'm going to use the HTTP GET verb. I'm going to pass in the URL /users/1. And then when I make that request, it is going to return a JSON result, which gives me all the details about that user. Similarly, if I want to update a user, I can use the put verb. And I'll make a put request to the same URL /user/1, and I'll pass in the body of my request what update I'd like to make. In this case, I'd like to replace that user with username John Doe and email johndoe@example.com. If I want to create a new user in REST, I'm going to issue a post. I don't know the ID yet, so I'm going to post to the root of that resource /users, and then I'm going to pass in the body the data that I want associated with that resource. So I want that resource to be created with Stefan May and Stefan@hellointerview.com. In REST, I can nest these resources if I want to. So if a user has posts, as an example, then I can retrieve a list of those posts by sending a request to get/users/id/post. Basically, I'm organizing my API around URLs and around verbs. Now, this organization can be a little counterintuitive to some developers because they're used to thinking in terms of function calls. So it wouldn't be appropriate for a REST API, for instance, for me to have /update user as the URL. That wouldn't really make sense in REST. And the reason it wouldn't make sense is because update user isn't a resource, it's an action. Instead, what I would do is I would make this put call. There are operations that you might think of as mutations or operations that need to be performed. And typically in REST, what you'll do is make those an update. So for instance, if I wanted to start a game that already existed, I would go and make a patch call that would update the status of the game to running from stopped or from pending users start. And what that's doing is it's basically changing my thinking from making operations to making updates to resources. REST is very popular, and it is, in some sense, the default that we would suggest for how you build APIs in system design. There is some overhead, and there's certainly some thinking that you're going to have to do in order to make this work, but it has wide generality. Everybody knows REST and is able to use it, and it's reasonably performant for most applications. Now, just like there were situations where we might want to move from the default of TCP to UDP for special applications, there are certainly instances where we might actually want to use a different protocol for our application layer. One example of this is GraphQL. In GraphQL, we're going to acknowledge some of the problems that exist with RESTful APIs and then provide an alternative for them. Let's pretend that we are designing a mobile app, and we've got this view that shows some profile information, some status information, and a list of groups that this user is associated with. Whenever I open this page, in a RESTful context, I need to make 5 or more requests to the server. This is a bit of a pain. First of all, it means that my page or my screen is only going to be fully loaded as soon as all of these return. And secondly, all of the overhead of establishing an HTTP request and serializing the information happens in each of these requests. This would be an example of something that we would call underfetching, where basically I'm not getting enough information in the response and I've got to go and make other requests. Similarly, I might try to solve this problem by basically creating a kitchen sink endpoint. So this wouldn't be a valid RESTful endpoint, but let's pretend I have a /everything you might need endpoint, and it's going to return my entire database of information. I've solved the problem of underfetching. Now I only need to make one request, but I've created this new problem in that this request is going to be really expensive to return, and it's going to take a long time. There's going to be a bunch of latency. And so GraphQL is really trying to solve this problem that very frequently happens when we're developing apps or web pages, where our requirements are constantly changing. We might want to add a widget here or change fields here. And we don't necessarily want to have to change our APIs on the back end every time that happens. It's mostly a front-end concern. So what can we do? The way that GraphQL works is it basically provides a way for the front end to describe the shape of data that it needs to retrieve. And then the back end is then able to figure out where to get that data so that it can return it in the way the front end needs. This might be a little small on your screen, but this is a GraphQL query that says get users with profiles and groups. We have the user's ID and username. Underneath their profile, we have their avatar and their full name. And then we're also, in each of their groups, we're going to have a name, description, category. And so our GraphQL response is going to return all of this data and nothing more. What GraphQL has done is instead of telling me about resources, I'm telling it exactly the view I want to materialize on the front end. And then the back end is free to figure out what details it needs in order to make this happen. Now, GraphQL in practice can be very useful. And it's really useful in those situations where A, your front end is changing all the time. You're doing experiments, the requirements aren't firm. Or B, when you've got lots of different teams, maybe your front end and back end team aren't connected. Maybe your front end team needs to connect to multiple back end teams and they don't have the same API that they're using to expose their data. But both those situations actually don't happen as often in system design interviews. In a lot of cases in system design interviews, you're the sole author of your system, and the requirements are going to be fixed at the start of the interview. So GraphQL is really useful in system design interviews in those cases where either A, your interviewer is not giving you all the requirements or somehow implying that they're going to be changing quickly, or B, you want to be able to design a system that specifically can support these arbitrary query patterns. Sometimes we'll see GraphQL used, for instance, as the endpoint for newsfeed style applications, where it's not always obvious all of the different views that the client may need to request up front. And we want to provide some flexibility for the front end and back end to negotiate those two pieces. Another example of a protocol where we might want to move away from REST would be gRPC or Google RPC. The way gRPC works, it's built on top of protobufs. If you're not familiar with protobufs, they're pretty simple. They provide a schema. It looks like a struct if you've written C or C++. And that schema provides a way to serialize objects into very efficient binary representations. So this JSON blob is 40 bytes and it contains John Doe and his ID. But in a protobuf representation, it's only 15 bytes, which is a massive savings. If my server is handling gigabytes of data, then I only have to use half of them. gRPC builds on top of protobufs to add this notion of services. I'm going to define a message that is the request and the response. In my service, I give an RPC endpoint, get user. It takes in my request, and then it returns my response. In some cases, this is the type for my API. This will compile into stubs that can be used for a wide variety of languages, from Java and C++ to Node, Ruby, even some esoteric languages. What gRPC does is it makes the serialization and deserialization of my inputs much more efficient. Whereas with REST, I was using JSON blobs, which actually need to be parsed. With gRPC, I don't have a lot of that overhead. And that means that gRPC services can be up to 10 times as efficient, 10 times as fast, or 10 times as much throughput as their REST equivalents. gRPC also adds some additional features that are useful for operating microservices at scale, like client-side load balancing and streaming and some rudimentary authentication. So the idea behind gRPC is pretty sound. It's basically how Google builds services internally. The main problem with gRPC is twofold. One, mostly external clients don't support gRPC. Web browsers don't support gRPC natively. And secondly, operating with binaries in between services is really efficient and very effective for the servers, but it makes it harder for devs and other teams to be able to debug the information that is being passed over the wire. Now, of course, there are solutions for this, and I would love for gRPC to be used more widely, but the reality is it's not used that often. So what that means in practice for system design interviews is that gRPC is, in some sense, mostly useful for internal services. I might have a client who connects to a web server, an API server over HTTP or REST. And then when I have some high performance bottlenecks on the back end, I can have my own controlled host communicate over gRPC. This is kind of the best of both worlds, where I get high performance interconnects for all of these hosts, but I get a language and a way of communicating with my clients that's widely accepted and easily debugged externally. In general, for interviews, I wouldn't suggest bringing up gRPC unless you were tightly optimizing for performance. But in those cases, having a setup like this, where you've got a hybrid of REST and HTTP and gRPC internally, can be the best of both worlds. So far, we've mostly been talking about requests and responses, which is going to be the vast majority of applications that you're going to build. But there are a lot of applications where you want to be able to push data to your user as it's happening. Examples of this would be like stock ticker updates, or maybe notifications that you want to send to your users. And in those cases, you can just go poll the API to make repeated requests, but that means that your information is going to be delayed by up to your polling frequency, and there is some overhead of repeatedly opening and closing connections or making those requests. So enter server sent events, or SSE. SSE is an extension on HTTP, so it's basically an HTTP request, but with one notable difference. With a typical HTTP request, our response is going to be consumed almost wholly. That's not exactly true, because there's a lot of websites and web browsers which will process the request as it comes in. But in most cases for APIs, you can think that I'm not really going to be able to process the response until I get everything. So if I was sending a list of events where they happen over the course of 10 seconds, I'm not going to be able to process those events until all of them complete and then get sent in this response. With SSE, what I'm going to do is include additional headers in the response, like chunked encoding. And then in the response, I'm going to use new lines to designate how each of the events are happening. And so what will happen is when my first event comes, I'm going to pass it over the wire as part of the first line of that HTTP response. Because of the headers, all of the proxies and other things that are handling that request are going to send that response right onto my clients. And my clients are going to immediately start to parse the response. What that means is that I basically have a way to unidirectionally push notifications from server to client. And the nice part about SSE is I can use the existing HTTP machinery. I don't need new infra in order to build out on top of SSE. Now, the downside of SSE is that those connections are going to be severed frequently. HTTP requests are expected to return in somewhere on the order of 30 seconds to 1 minute. And so most routers and proxies are going to time out or disconnect requests that exist for longer than that. What SSE will do in those cases is automatically retry. Most of the clients, like event source, will open up a new SSE connection. And what they'll do is they'll pass the ID of the last event that it received, just in case one event happened between the time that it was disconnected and the time that you reconnected. But it's a bit of a kludge. You're basically existing on this connection that is constantly pushing responses, that is periodically severed and then re-enabled. That said, just because it's kludgy doesn't mean it doesn't work, and many applications can use SSE. It's a great option if you need to get updates to a UI for a short period of time. So as an example, if you're making a request or you're buying a product and you want to know the status, that might evolve over the next 15 seconds. It's also really useful for AI applications where you might want to stream tokens or responses back to the user because they take a while. It might take 30 seconds for your full response to actually be built out. So server-side events built on top of HTTP and allow you to have longer running requests that the server can push events down to the client. SSE can be super powerful for those push notifications, but in some instances, we actually need bidirectional communication. Our clients need to be pushing to the server in as much as the server needs to be pushing to the client, and we care a lot about latency. In those cases where we have high frequency updates and bidirectional communication, that's where we're going to bring in WebSockets. Now, I want to offer a caveat before I get into WebSockets that I oftentimes see candidates use these inappropriately. WebSockets are really powerful, but they also require a lot of infra, and it may be more appropriate to think about a polling-based solution or an SSE-based solution before you launch into a full-tilt WebSocket solution, especially if the functionality that you're designing is pretty narrow. So like getting an update on a bid for just a general browser of the page. That probably doesn't mean you want to open millions of WebSocket connections. But where you need WebSockets, they are going to be very powerful. And the way that WebSockets work is basically by simulating a TCP connection, but by making it accessible for browsers and other clients. So a WebSocket is basically just a way for you to exchange binary blobs that come in on the same order and are in some sense guaranteed to be delivered reliably. When you design WebSockets in a system design interview, you're typically going to talk about an API in terms of messages that you're sending. Because these aren't request and response, you don't typically have that function style setup where you can say, here's the input and here's the output. Instead, you'll say, hey, I'm going to receive a ticker update notification to my client. And then on my client, I might send a subscribe or an unsubscribe. Now, it doesn't eliminate the possibility that you have a message that you get received of a subscription accepted, as example. But you shouldn't design WebSockets with this intention of having a lot of request and response style of operations, just because that's really not how WebSockets are designed. If you want that request response functionality, you're better off using HTTP. WebSockets in general are going to involve a lot of state for your application. If you've got a connection, a WebSocket connection, that means that connection needs to be active for as long as the lifetime of that WebSocket connection. So if I have a WebSocket connection to a server and that user is going to be around for an hour, I need a way of keeping that server alive for as long as that connection needs to be alive. This can really play havoc on applications where you want to do deployments or you might have failures. So in a typical WebSocket setup, you want to have some sort of fallback so you can reestablish connections or move them between servers. Typically in system design, you want to minimize statefulness, but WebSockets are inherently stateful. So the way that you're going to handle them in an interview setting is usually by having something on the periphery or edge of your design that handles the WebSockets and exposes methods that internal services can call. You might call it a message broker or a notification service, but essentially you'll have all of your users connect via WebSockets to that service. And then that service will make requests to your internal services, and those internal services will then send messages back via WebSockets. We've got a lot more detail on this pattern in our real-time updates guide on the Hello Interview website as part of the premium offering, if you're interested in getting into more detail. The final protocol that we're going to talk about is WebRTC, and this is by far the most unique and the most niche protocol of the group. WebRTC, unlike all the other protocols, runs over UDP as opposed to TCP, And it's really used in those places where you either have collaborative editors or you have audio and video connections between clients. WebRTC is unique because it's a peer-to-peer connection. That WebRTC is a way for clients to connect with one another, which makes sense if you think about video conferencing or collaborative editors. The way that it works is pretty complicated, but let me give you just a flyby of the typical setup process. And then I'll defer to some reading that you can have in the write-up of this guide. That'll give you more detail if you want it. So what will happen is our clients will first connect to what's called a signaling server. It's basically a centralized server that maintains knowledge about all of the clients who are connected to one another and is able to exchange information. The signaling server doesn't handle the bulk of the information. It's not handling video feeds. It can handle a lot of clients, even though the aggregate transmission over WebRTC between clients might be pretty high. After the client connects to the signaling server, it's going to learn about its peers and basically decide which ones it wants to connect to. The next thing that it's going to do is connect to what's called a stun server. The problem is most clients don't accept inbound connections. This would usually be a security problem. If you can imagine, if you connected your laptop and suddenly hackers could go and connect to your host, you might have issues as vulnerabilities are uncovered. So most clients aren't exposed to the internet. They're clients, they're not servers. But in this case, if we want these clients to connect to one another, we need to create a way for them to do that. And this is typically done through a process called NAT hole punching. I definitely won't be able to get into detail about it, but this stun server helps us to both find an address that we can use so that our peer can connect to us, and then also facilitate that hole punching. After we've got an address and we're ready to go, we can share the information between our peers so that they can connect to one another. And then once they've connected with one another, they can send information over that UDP connection to each other. This would be where you would do your video conferencing. In the rare case that they're not able to establish a peer-to-peer connection, they can use yet another centralized server. They call it a turn server that basically would allow clients to bounce requests to one another, which is obviously the least efficient and least desirable outcome. WebRTC sounds pretty seductive because peer-to-peer seems like it could be really powerful, and it can for the right application. But a lot of candidates in system design interviews use it unnecessarily, so I would generally avoid it, except if you're doing audio and video calling, in which case it might be worth bringing up. The other use case that's acceptable is collaborative editors. As an example, you might use a peer-to-peer connection to exchange updates on a shared document. And in that case, you would probably use what are called conflict-free replicated data structures, or CRDTs, conflict-free replicated data types, in order to share the document state in a way that is amenable to peer-to-peer connection. If that sounds confusing, you should totally ignore it because it is, while an awesome design and one that you may be able to read up on, also probably not necessary for 95+% of interviews. So for WebRTC, think about it as when you need to facilitate audio and video calling. This wraps up the primary protocols that you're going to see in system design interviews. And I hope you see that there is a wide variety of applications that you can support. Streaming applications through WebSockets and SSE, high-performance backends through gRPC, flexible front ends through GraphQL, and then the jack-of-all-trades RESTful APIs. In system design interviews, you're usually going to be scaling. Oftentimes the questions are, how can you design a system that works with lots of users or lots of data? And that can go in one of two directions, either vertical scaling, where we're going to use bigger hosts and more hardware, more memory, more CPU, or horizontal scaling, where we're going to duplicate our servers and find some way of balancing our requests and our data between them. Vertical scaling is by far my preference, and I think a lot of people are ignorant of how effective modern hardware can be. They're kind of stuck in this world of the early 2010s where Google needed to use commodity hardware in order to get anything done. In a lot of cases, you can find servers with terabytes of memory, and you should use them because I think they'll be effective. But in interviews, interviewers are typically expecting that you're going to require some form of horizontal scaling. And so it's worth us talking about some of those implications. The most important implication of horizontal scaling is you introduce this problem of load balancing, where I've got a client where previously I could connect to a single host. Now I need to connect to multiple servers. And load balancing serves two purposes. One is it spreads the load, so that way, I can actually handle way more traffic than a single server could handle. And the second is it facilitates high availability. Now, if server 1 goes down, theoretically, my client can connect to server 2 and server 3. When a lot of people hear load balancing, they think load balancer, like a dedicated device that's going to spread load. But that's not the only way to do load balancing. There's theoretically two ways that we can do this. One is we can do client-side load balancing, and the other is that we can use a dedicated appliance. With client-side load balancing, what we're going to do is have the client be aware of all the servers that they can connect to. They will query some sort of registry that will tell them about the existence of all of the servers. Another path is for them to actually query the servers themselves. So they might have a reference to one server, and they can ask that server about other servers. That's how Redis cluster works, for example. And the reason that client-side load balancing can be really effective is because it doesn't introduce an additional hop of latency. If I have client-side load balancing, then I can directly send my request to the server that's going to handle it. I don't have anything in the middle. On the other hand, client-side load balancing requires that the clients get updates about the servers that exist, and I don't get to employ sophisticated load balancing techniques. I can't expect that my clients know, for instance, about the state of servers all the time. So you're going to use client-side load balancing in scenarios where either A, you don't have many clients, which is oftentimes the case on internal-facing microservices, or if you have lots of clients that you can tolerate update delays. An example of the latter is DNS. DNS is when we make a request to go and resolve a name like hellointerview.com to the IP addresses of the servers, we're going to get a list. That list will be randomized or shuffled. And we are going to first hit the first server on that list. And then if they don't respond, we'll hit the second server on that list and so on. And what this is going to allow the aggregate consumers of DNS to do is handle the load balancing by themselves. But the tolerate update delays is really important for DNS because DNS is heavily cached. If I make an update to that IP list, it might take anywhere between 5 minutes and a day for all DNS servers to receive that update and then to begin serving it to their clients. So it's not a great solution if I need to be able to react rapidly, either to scaling events or other issues that I might encounter. So for system design interviews, client-side load balancing can be very powerful, and it's definitely a tool for your arsenal. Use it for internal-facing microservices. That's a great place for it. gRPC supports it natively, which is an awesome feature that you can use. But generally speaking, favor a dedicated load balancer in those cases where you need to be able to work with external clients that need to get updates relatively quickly. In those cases where I need to use a dedicated load balancer, I'm going to insert an appliance between my clients and the servers that I want to load balance. This appliance can be either hardware or software. So like F1 Networks has load balancers that scale up to hundreds of millions of transactions per second. Whereas software load balancers like HA Proxy or Apache may scale to 1 million transactions per second. You also obviously have cloud offerings like AWS's application load balancer or Elastic load balancer. You have lots of options. What will happen is when servers are initially spun up, they'll announce themselves to the load balancer saying, hey, I'd like to receive traffic. The load balancer will then make health check requests, trying to determine whether the server can respond to the request that it's trying to load balance. These health checks can either be very shallow, so like, can you take a connection, a TCP connection, to very deep, like, can I look at the response from this HTTP request and see the status code? These are all usually configurable parameters that you have on the load balancer itself. But the important thing is once your server has returned healthy sufficient number of times, the load balancer will start routing traffic to it. And then once it's unhealthy or stops responding, then the load balancer will stop sending it traffic. Now, the way that load balancers balance that load is also configurable. There's a lot of different algorithms that are in use. The most common ones for stateless services, like HTTP servers, or most applications where you're using simple request and response, is to either round robin or randomly allocate the requests. And the nice thing about this is if we assume that the requests themselves are going to take a random amount of time, then we'll get approximately even load across my servers, and my load balancer doesn't have to do a whole lot of work. The other way that we can allocate requests is by using least connections. So we can look at all the servers and find out how many connections I already have open between the load balancer and that server, and then only allocate new connections to the server that has the least connections. This can be kind of nice in those scenarios where I have a new server that I've introduced, I'm scaling up, and I want to make sure that new connections are going to that server until it's approximately even with the rest. If I was randomly allocating, it would take a longer time for that new server to kind of get up to the same speed, especially if my requests take long. Another place where least connections can be really useful is if I have long-running or stateful connections, so like WebSocket connections. WebSockets might last for an hour. And in those cases, I can have really uneven load across my servers because some of those requests might take just a few minutes and some of them might take a very long time. And so least connections is going to provide some guarantee about how evenly I'll allocate amongst them. Another consideration that I have when I'm choosing load balancers is at what level they're operating at. So the two examples are a layer 4 load balancer, which operates at like the TCP level, or a layer 7 load balancer, which happens at the HTTP level. Let's talk about what each of them looks like, with the idea that in some cases, your interviewer might want to know which load balancer you've chosen. The way a layer 4 load balancer works is it initiates a layer 4 connection for every inbound connection that it receives. So when my client is trying to connect to my service, it's going to create a TCP connection to the load balancer. And that load balancer is going to create a parallel TCP connection to the server. For a layer 4 load balancer, I can kind of pretend like this load balancer does not exist. It's as if the client has a connection directly with the server, and that connection that I have to the load balancer is just a proxy to that connection with the client. The nice thing about layer 4 load balancers is they're really high performance. The layer 4 load balancer doesn't need to do a lot of thinking. It doesn't need to look at packets. All it needs to do is when it receives a new connection, to create a new connection with the server, and then any packets that it receives on the inbound connection, it pushes to the origin, or basically the servers that it is load balancing. An alternative to a layer 4 load balancer is a layer 7 load balancer. Amazon's application load balancer would be an example of this. And what this load balancer is going to do is instead of only accepting TCP connections, it's actually going to accept, say, HTTP requests. It's going to accept requests at that last layer, at layer 7. And then what it's going to do is it's going to choose an arbitrary server based on its load balancing algorithm that it will send that request to. So for the server, it's actually not as straightforward whether the connection that it has with the load balancer is the same one that it has with the client. The layer 7 load balancer might have only a few connections to the servers and many connections to clients. Now, layer 7 load balancers can be a little bit more expensive because they need to basically be able to handle the application layer responses. So they need to be able to handle a full HTTP request. But what it means is that if I had a single TCP connection and multiple HTTP requests that happened over it, I can fan out those requests to all of the servers. I don't have to necessarily send them all to one server. So it can be very effective. Layer 7 load balancers aren't going to be appropriate in those cases where I have a connection-oriented protocol. While some layer 7 load balancers will, for instance, support WebSockets, for the most part, layer 7 load balancers aren't appropriate in those cases. We're actually going to want to use a layer 4 load balancer. But in those cases where we can accept a bit of a performance hit, a layer 7 load balancer is going to provide a lot of functionality, routing options, the ability to terminate HTTPS. Whatever we want to do, we can probably do it with a layer 7 load balancer. So it's going to be the default and the thing that we would recommend in most instances. The exception in system design interviews is if you're using WebSockets or any stateful connections, you probably want to use a layer 4 load balancer, and your interviewer may ask you questions about how that is set up. We are almost there. We've covered our networking 101, gotten through all of the major protocols, and talked about load balancing. For the last part of this video, we're going to do some deep dives into questions that you're likely to field in the interview and talk a little bit about the networking ramifications of them so that you're prepared for them. First, let's talk about regionalization. Typically, in a system design interview, you're going to be asked to design a system that works across the entire globe. And when we talk about networking across the globe, we have to deal with the laws of physics. If I wanted to make a connection between London and New York, the speed of light can only travel so fast in a fiber optic cable on either side of the Atlantic. So from a practical perspective, I'm going to have about 80 milliseconds of latency no matter what I'm doing. That could be a problem if I need to make lots of requests back and forth across the Atlantic. So I need to figure out what I'm going to do about that. Another problem that we typically have is in global scale systems, we have global scale traffic. And that can oftentimes be a challenge. For instance, you're asked to design a service like Uber, which operates in many locations. In a lot of cases, we can simplify these problems by recognizing where there are some neat partitions in the problem. As an example, with Uber, what I can do is recognize that riders are typically only requesting drivers in cities that they're currently in. I'm not going to be requesting a London-based driver from Seattle, as an example. And that really simplifies the problem. What it means is that I can take my system design and duplicate it in the relevant cities that I'm going to be conducting business. Those cities can operate at a much smaller scale, and I'm going to get all of the benefit of a regional network. All of my writers are going to get near instantaneous responses because my system is nice and close. Now, the reality is having a data center in every city that I'm operating in is probably impractical. So what companies are typically going to do is they're going to have data centers that are close by, that are in regions that are associated with those cities. So I'll batch together all of the East Coast cities and all the West Coast cities. There's a couple things to keep in mind as you're regionalizing services. One is that we want to keep the core of your data and processing as close together as possible. It's called co-locating your data. And the reason for that is, while one request might come in from your user, let's say from London all the way to New York, I'm probably going to make many requests back and forth between my web server and my database in order to figure out what the response is before I go back across the network. It would be a really silly idea if, for instance, I put my web server in London, so that way that hop was nice and short, and then I had a long hop back and forth to the database before I could answer a question from my user. Another thing that we want to do is we want to get our services as close to our users as possible. Now, I can move my web server and my database to London, but I'm going to run into a few problems. First of all, I can't always depend on moving my data around the world. I might be able to do this in the Uber case, but in the Reddit case, I have users in China who are accessing, actually, can China access Reddit? I'm not sure. I have users in Japan who are accessing posts from people that are created by people in the UK who are interacted and commented on by people in the US. I, in some sense, need my data to be everywhere. So you've got a couple options here. One is you can have that data be local to where it's most likely to be used, even though people in the UK are going to access data in the US. Maybe they aren't accessing it as frequently because of the time zone differences, in which case I can partition my data globally. Another thing I can do is I can replicate my data. I can have it to where when I write to the database, I store it locally, but I'm going to make sure that that gets replicated to other regions so that they can read it quickly. This inherently introduces a lag. It means that there's going to be some time between when a post is created in the US and when it's available in Europe, but that might be okay for my purposes. The last thing that I can do is employ what's called a content delivery network, or a CDN. And the idea behind a CDN is pretty clever. You can think of CDNs like a cache. So what we're going to do is we're going to dot the globe in various cities, and most CDN providers have hundreds of locations. They call them edge locations. And those are going to be servers that users are going to connect to, kind of like gateways. So when I want to make a web request, I'm going to find the edge node that's closest to me, and I'm going to make a request to it. But the magic of a CDN is they can serve a lot of the requests immediately. So if, as a cache, someone has recently requested the front page of Reddit, and it's already sitting on my CDN, then I can return that to the user immediately. I don't have to do anything, which saves me any additional latency that I might have going over to the database or the web servers or wherever that data is located. Quite convenient. The other thing that cache does is it reduces the load on the back end because it's a cache. Now, of course, not all data can be cached. And in those cases, what will happen is that edge node will make a request to the server that can actually service the request. That's called the origin server. And in that case, the CDN is mostly acting as a proxy. It's just an intermediary between you and the backend servers. But regardless, the key concepts here for regionalization stand. What we want to do is we want to try to partition our data and keep it as close to our users as possible. And we also want to make sure our processing and our data all happen in approximately the same location. The next practical area that you're very likely to see in your interview is how to handle failures or faults. A lot of times people think about what happens when the server goes down, but they don't think about what happens when the network goes down or there's a partition in the network. There's a lot of advanced topics here, especially dealing with split brain in databases and how to handle network partitions. But let's talk about the basics first. First, when clients are connecting to a server, we want to make sure that they eventually time out. What would be the worst possible scenario is for me to make a request to a server, get some acknowledgement that it's in progress, and then never hear back from that server again. That client will be waiting forever. So we want to always put some sort of sensible timeout on the request to make sure that we eventually give up and send an error message to our users. The worst case scenario is I set my timeout to something short, like 3 seconds, so I can get my error messages to users fast, and the server takes 4 seconds to respond. In those cases, no matter how much I try, I'm going to fail. And so we need to make sure that our timeouts are long enough that our servers can respond, but also not so long that it doesn't really serve its purpose. Now, when there's a timeout or when there's some sort of failure, typically what we're going to do for robustness is we're going to retry. And this is kind of a tried and true way to handle failure in systems. And the idea is really simple. I make a request and it fails. I'm going to try again 5 seconds later. A naive approach would be every 5 seconds I go and make a retry. And it's naive because A, the server's probably not changed, and B, it suffers from this bunching behavior. So if, for instance, I have a service that can only handle 2 transactions per second, but I've got 3 clients who are all trying to make a request at the same time, I might have them fail. So both my red, green, and blue clients simultaneously make a request, they all fail. They all have a policy to retry again in 5 seconds. And in 5 seconds, they retry again and they fail again. And then they fail again in 5 seconds. So we're going to use 2 tricks in order to fix this. The first is we're going to employ what's called backoff, oftentimes exponential backoff. What this means is that the time between our retries is going to increase. And so maybe the first time we wait 2 seconds, and the next time we wait 4 seconds, 8 seconds, and maybe we give up then. This kind of has a two-sided purpose. Our first retry should probably happen pretty quickly. What we don't want to have happen is for our users to wait for a long time for something that was transient. Maybe a solar flare hit a disk somewhere. But once we get 2 failures in a row, it's pretty likely something substantial is actually wrong, and it's going to take some time to recover. So backoff basically gives us a way of spreading out that load so that the server is not getting, or it's getting, in this case, half as many requests in the same period of time as it was previously. Now that's nice, and we're spreading out that load and potentially giving the server a chance to recover. But what we aren't doing is handling the synchronization problem. Basically, every request that we make is also happening alongside green and blue. And so every single time we're still tripping over that 2 requests per second limit. What we're going to do here is we're going to add something called jitter or randomness. For our red client, we're going to delay a little bit. So instead of 2 seconds, maybe we do 2.5. And for my green client, maybe I do 1.9. My blue client, quite a bit longer. And what that's going to do is ensure that the synchronization doesn't happen. These are all spread out over more time. And because they're delayed a random amount of time, successive retries are also spread out. And what we see is that this continues to distribute across the timeline. What this is going to do is kill that synchronization. It's going to distribute the load and theoretically give the server a chance to get its bearings so we can actually have a successful request. Now, that sounds good. And generally speaking, in interviews, the gold standard for you to refer to when you have connections between servers is you want to have timeouts and retries with exponential backoff with jitter. That's kind of what you could get away with in most sessions. The last deep dive that I want to talk about are cascading failures. These are typically seen more in senior and staff level interviews, in part because senior and staff level candidates have probably seen them before and have been burned by them. If you've ever been up at 3 a.m. and are on call with a service that just won't come up for a variety of reasons, you're probably very sensitive to cascading failures and some of the implications they have on your sleep and your life. And you're going to want to make sure that people you bring into your company also have some of that experience so that they don't make similar mistakes. The idea with cascading failures is sometimes problems in one part of the system can create problems in another part of the system. So let's pretend that we've got a service here where server A makes requests to server B, who queries the database. Everything is going fine for a while. Then one day, our admin or our ops guy decides we need to back up the database. So he triggers a database snapshot. Now, suddenly, our database is operating at 50% of its normal efficiency. Because our second server wants to make sure that it's robust against failures in the network, they put timeouts on the request to the database. And suddenly, because the database is returning 50% slower, it is failing those requests. Like a good service, it's retrying those requests, but those retries are also failing. So the server will try those requests 3 times over progressively longer and ultimately give up and return a failure. Server A is doing the same thing. It makes a request to server B. Some of those requests are timing out. For those requests that fail, it's doing it again. So what we're going to see here is because of the snapshot that degrades our database, our first server is going to start to fail, and our second server is going to punish it for suffering under the underperformance of the database. So server B is going to go down. And what happens next? If we think the problem was with server B, we're going to just try to start it up again. But when we start it up again, we're going to see the same problem. The database is unresponsive and server A is still hitting it with as much traffic as it can. So what we need here is for server A to give server B a break. So that way server B can give the database a break, which hopefully someone notices that the snapshot is happening. The way to deal with this is typically to implement what's called a circuit breaker. And the way that a circuit breaker works is kind of like the circuit breakers that you might have in your house. When the electricity going through your wires exceeds a certain current, the circuit breaker flips off and it requires human intervention. A typical circuit breaker in software is going to trip when a failure exceeds a certain level, and then it will periodically reset itself. And so what will happen is server A will say, server B is obviously not handling many, if any, of my requests. I'm going to temporarily pause. I'm going to fail all of my requests. I can't answer without server B, and give it a chance to recover before I try again. From an operational perspective, this gives me a chance to notice that server B is slow. It's not answering those requests quickly because of the database. And then I can go and fix the database problem. Then when the database problem is fixed, server B starts responding in a reasonable amount of time. the circuit breaker automatically resets and server A comes back online. Circuit breakers build robust systems by basically failing in an obvious way. You'll obviously want alarms on these circuit breakers so you know when they trip, but you'll know that something is egregiously wrong, and you'll also know that you can probably handle this downstream. If this is tripping, it means server B is not living up to expectations, and you don't have to worry about server A punishing you while you try to bring it back up and fix the problem. Okay, folks, we covered a lot of ground, and I want to summarize before we end the video. So we started with Networking 101, talking about the OSI model and the layered abstractions that are networking protocols. We started with layer 3, which is our Internet Protocol or IP. We talked about public and private addresses, where public addresses are for the services that are internet facing, and private addresses are what you're going to use internally for your microservices. Then we moved on to layer 4, where we have TCP, UDP, and QUIC. TCP is the default, and it's a good recommendation for what you're going to use, but you may run into problems where UDP is more appropriate, namely those situations where you can tolerate some loss and you need very high performance and low latency. On top of layer 4, and predominantly on top of TCP, are layer 7 protocols. And we touched on a lot. We touched on HTTP, which is the backbone for a lot of the API protocols. REST, which is our default and our suggestion for what you use in a system design interview in most cases. gRPC and GraphQL are useful in narrower circumstances where you are very concerned with performance or you need a lot of flexibility in the case of GraphQL. Then we talked about SSE being how servers can send messages down to clients, WebSockets that enable high-frequency bidirectional communication, and WebRTC, the peer-to-peer protocol predominantly used for audio-video calling, but also can be used in narrower circumstances for collaborative editors. We then moved on to load balancing as the discussion. We talked briefly about horizontal and vertical scaling, and we talked about types of load balancing strategies. Client-side load balancing is typically for internal microservices and offers really great performance when you've got a limited number of clients. When you need to go externally to a larger number of clients, you've got your dedicated load balancers, which can be software or hardware. And typically you'll choose between a layer 7 load balancer or a layer 4 load balancer, where layer 4 is most appropriate in those circumstances where you need really high performance or you have connections, as in the case for WebSockets. Finally, we went through a bunch of deep dives that you might encounter in your system design interview. We talked about solutions for regionalization, including CDNs. We talked about timeouts and retries, and the gold standard here is retries with exponential backoff and jitter. And finally, we talked about cascading failures and how circuit breakers can enable you both to respond when those failures are happening, but also self-heal and recover quickly. These form the basis of most of what you need to know from a networking perspective to be effective in a system design interview. There are obviously deep dives that we can go into for specific problems, but we find that this will get you 90% of the way there for most of the interviews that you have. And I hope this has been a useful overview of this core concept. If you've got questions, leave them in the comments. We always love to hear your feedback. And then if you want to read more, get into more detail, you can find for free this deep dive on our website. I'll link it in the description, as well as other supplemental material that we have as part of Hello Interview. Really thank you for watching. All the best.